All right. Thanks a lot, Alan, for the kind introduction. So essentially today I want to share with you a couple of explainability tools that we deliver in the last year, essentially. And I want to combine with one of those about one of the things Alan was mentioning before. So sometimes explainability really needs to be tied to the domain where it has to be applied. And this tool is based on reinforcement learning. We're going to see it in a minute. And the other tool is a little bit more generic and deals with essentially time series forecasting. Now, before going into this, like you see in the title, the talk deals with 6G mobile networks. So just an announcement, I don't want to annoy you with details of how mobile networks work. I'll try to keep it as simple as possible, but you will excuse me, and I really need at least one slide to give you the motivation why we are going towards this end. Basically, 5G mobile networks, the one we have right now, basically have been defined with the objective of connecting things together. Think about Internet of Things, all these number of devices that have to be connected all together, and 5G really strives to deliver that amount of connectivity. Now, going to 6G, that is the next generation of mobile network that is going to be, the rollout is foreseen basically for 2030, we want to move forward and we want to have connected intelligence. Why? But this is yet not enough, because to connect all this amount of devices, smart plugs, and etc., you basically want, we move the focus onto the devices, but the network architecture has evolved not as much. But with 6G, there are a number of enabled technologies that have defined and reshaped also the radio part that essentially allows to connect our smartphone with one of the access points antennas that can be in buildings or on top of the roofs. And also the core part of the network that basically no one sees, but is basically responsible to connect all this amount of base station, imagine the scale, number of devices, base station, metropolitan aggregation, and etc. I will give you a flavor. In the physical access, where you see phi here, basically we are modeling the way we propagate the transmission over the air through the wireless medium. Here, the main innovation will be that with AI, it will be possible essentially to self-configure the modulation that has to be used for the transmission, to perform self-error correction, up to the medium access layer, when basically we define and decide how many resources we give for each transmission, all the way up to, for example, self-configure and self-manage and automate the network architecture itself. Just to give an example, and with this I'll try really to stop with the technical details of 5G, a single 5G base station contains, roughly speaking, in the order of thousands of parameters that are categorical, numerical, and etc. And these have to be configured when you deploy a new base station. And as you can imagine, since in the last year there has been the 5G rollout, the network operator have been really concerned about how this really scales, because it's really complex. Imagine you deploy a base station in downtown or you deploy a base station in the middle of nowhere. That's way different, because all those parameters have to be configured in a completely different manner. So that's basically to motivate why 6G network is said to be AI native. And given this, now I'll go through the explainability techniques. This work is called Explora, and like I mentioned, is a work that really tells that explainability has to tie it to the specific domain. Here, with colleagues at Northeastern University, we work towards explaining a deep reinforcement learning agent that they developed. I'm going to this in a minute, and basically, I want here just to highlight that at Northeastern University, there's a testbed, very nice, very important for us, because allows programmability of experiments. That said, because this testbed is basically composed of software-defined radios that allow to model the wireless channel, and this software-defined radio can actually be basically used with software that basically defines the 5G stack. Like this, we can basically perform experiments programmatically and repeatedly. This has enabled the guys essentially to create a deep reinforcement learning agent that performs resource allocation and at the same time the scheduling policy. Basically, if we have to decide among how many of you have to receive a certain amount of physical resources, that's the scheduling policy that is going to assign this. Now, this agent at the same time takes these decisions for what is called slices. Slices basically are a logical partition of the physical network that strain to deliver specific type of services. Here, for example, we have the 3 slices we've used. When you see EMBB read like video, your YouTube watching. EMTC read like machine type of communication. For example, your Roomba in home delivering statistic about how was basically cleaning the environment. URLC read like mission critical communication. For example, communicating with a drone for mission critical services. Now, this agent basically takes in input, you can see in the right of the picture, statistics, KPIs that come from the users, and users can be variable. That's why we have an autoencoder that basically creates a latent representation of all the information these users are providing, that are basically KPIs that tell about the transmission bitrate, number of packets, and the buffer size. With this compact representation, the agent basically, based on the previous resource allocation that you see on the top, takes a decision. And this decision impacts these 2 different things, the resource allocation and the scheduling policies for all the slices, all the 3 slices together. Now that's complex. Also, the reward function will come together later onto this because that's very important, is complex because basically it takes into account all the 3 components, but it's not monotonic. So we want to maximize the transmission bitrate, maximize the number of transmitted packets, but minimize the amount of data you keep in your buffer because that is a proxy for being quick. That is very important for URLC type of communications. Now, I came there to start analyzing and provide explanation, and I'll give you a line of thoughts. I wanted to look into what exists in the state of the art with different approaches. I look into using SHAP, and we'll see later in a minute issues with SHAP. And that's basically a technique that basically ranks feature importance. And I also wanted to look into decision trees as a surrogate, an interpretable model to substitute to this very complete agent. Issues with the decision trees. I tried to apply it to the single slice, to all the 3 slices together, and all the times the issue was that trees were scaling up and were very difficult to manage. Coming to SHAP. I tried SHAP, and the problem of these 2 techniques actually is that you actually can apply them onto the agent. And the problem is that, let me just go back 1 second, you don't get back to the actual input because the autoencoder masks this input. So that was the real issue. And SHAP, when I tried to apply it, was basically providing feature relevance of the outputs of the autoencoder that you see on the bottom part of the plots. And in the top, you basically see the decisions that are the resource blocks that are being scheduled and the scheduling policy. Now, SHAP is nice because it actually provides us with a pattern that I was basically looking into a different number of experiments, different configuration, and the same pattern was there. Anytime there's low importance that you can see in blue, dark blue on the bottom plots, basically there was a change in the physical resource block allocation. This is nice, but it's very hard to use from the perspective of a network operator, because imagine a network engineer, you go there and give him this, and he doesn't know what to do, essentially, because this is not a network quantity. He knows that this is important, but this is a latent representation. There's no connection with physical, with a physical meaning. Plus, there's another problem. I try basically to understand how much complex was to compute SHAP over this deep reinforcement learning agent, and turns out that basically the times on different GPUs were really high, with a very low number of users. Up to 4 users, basically this was taking 26 hours to compute that relevance. So that's really not applicable. And this comes to our intuition and our approach that is called Explora. Explora is a framework because basically delivers from one side explanation for the agents, and for the other can also refine the action decision mechanism that the agent. For creating explanations, we use attributed graphs. Attributed graphs are a popular technique, and what we do basically is that we encode the action as nodes, and then in the attributes, we encode the effect of the action for each individual KPI. That, for example, are bitrate, number of packets, buffer size. So we don't have the link that goes from the prediction back to the input, but for DRL, is to look at what that basically means on the state. We have been in Explora. I don't need. I want to give you just of what it means to build a graph. Is basically for a given amount of, and then basically we have like understanding what are the effect of the components. The first part is the scheduling policy. On the right hand side, there's the scheduling. On the left hand side, there's basically the physical resource block been defined for each of the slices. At time, the action, and we record basically T0 plus delta for each user the action. Then the agent changes and takes a different action. We process. At T2, the agent takes again the action was taken in T0, and we record that. Basically, it allows to create the attributes, the distribution of the effects that the agent you might say this doesn't scale because you have to record a number of information. And there are techniques to prevent that because, for example, you can prune the graph whenever those nodes have not been seen for a certain amount of time, and the same thing happens for the others. Here's a graph for one of the slices. You can see, given that we have this multimodal action that basically at the same time the decision mechanism impacts two different choices, the scheduling policy and the physical resource block allocation, we can see that in the graph we have a certain number of classes. We have self, where basically the same action is being repeated over time. We have a class that is semi-physical resource block allocation when the agent only changes the scheduling policy. We have distinct when we basically change at the same time. We have same scheduling when it only changes the physical resource block allocation. And now with all this information, we can see which is the type of explanation that we can get. Now we have tabular data because what we do is to look into the different nodes and study the transition. Means we look at which is the consequence of gene action over time. We can study this basically by just looking at this between the distribution of the individual KPIs. And the individual KPIs are driver quantities. For example, that one agent and one slice, we really see what the agent is doing when it takes a certain class of action. The class of action, same physical resource allocation, is meant to maintain throughput stable, which makes perfect sense from the perspective of network expert. So that's how basically to create explanations that are network aware. Even that here we have tabular data because we have for individual class the specificities in KPI, create decision trees on top of it that basically tell with which the classes have been created and the agent arrives at decisions. The last thing, as for Explorer, is a framework because it also allows to improve what the agent does. It's very complex, and it's one of the things I'm more proud of. Whenever an agent takes a decision, is because it has a certain state and thinks that that's the best decision possible, right? Now, since we have created a graph for enforcing that action, we can go into the graph, exploring the graph, and maybe action. This is valid only for our case, so if you want to look at it, try it, but be cautious, because in our case, we are looking at physical quantities that vary over millisecond timescales. This means basically over consecutive timescales, there's not be so much of a change, and therefore, whatever we look into the graph, we have information stored in the graph, is recent enough so that we can do the approach. The approach consists of looking into the graph and take a policy that, for example, allow us either to choose a that, for example, will bring us a higher reward, and that basically translates into looking into nodes of the graph, or taking an action that generates, for example, a higher throughput. Now, with this, we can see that this is actually helpful. If we take, for example, the concept P1, we can basically improve throughput that the is providing to the network. And it's very important from the perspective of network operator because basically allow to define programmatically intents in which we want to control the operation of the agent itself. So just as takeaways and summarize, Explorer generates network-aware explanation. That's very important. And we know that we can also revisit the action decisions so that we can improve basically what the performance that the agent is taking. We make the code public so you can take a look and use it. And now we move very quickly to the second tool that deals basically with series forecasting, full in-house work. And the context basically is about creating and automating the process of operators. For example, if you know in advance which is going to be the traffic load that our together create at a certain amount of time for the base station, you can basically perform intelligent traffic balance, steering. This is really an advantage for network operators. In this context, we have basically used a number of data sets. One of them is published basically from an initiative was taken by Italia operator 13 in the Arab Middle. We use other data sets. One is from a metropolitan city in Europe that we cannot because we have NDA with that operator. And another one was basically collected by ourselves in Madrid, and you can download it in case you are interested in. It's all about code, and we have used well-known models from LSTM to more ones, the linear patch TST, and are all models that basically essentially sequence to sequence. So you have a sequence of values, and you want to pick the future 81 or a number of values in the future. And we basically legacy explainable AI techniques like shallow LRP, and I show usually to non-expert basically what happening. You have your look back, and basically up of LRP will assign relevant scores. For example, a high relevance is given to items that are very close to the forecast in this case, and also in very nice. It has a problem, and this is basically we have looked for all the datasets we have, the entire. We have built a profile for the LRP scores and scores. We are them and put in relation with the actual time series, the actual traffic load. And that's basically happens, that the explanations are not univoc. So we cannot, like certain cluster of a certain profile, we cannot match a certain profile of traffic space. Basically it means that if we use this within a real network operator, right now, an amount of traffic, and don't really know whether this explanation is meaningful or not. So what we did was to basically create a tool that overcomes this issue, call it AI chronology, and basically that's the main critical that is it's something that is more univoc based. So what we did in a nutshell was to enrich that semantic. We use basically the Gramian angular field, that is a time series imaging technique, onto look back and try to seek for linear correlation with what the legacy explainable techniques give us, that are relevant scores. Basically, an output that is an image that are basically correlation coefficients, and we study those. Basically, we move the problem from is not unique to something that becomes unique, and it's a little bit complex to understand and to process. But what we've seen is something very useful. So this is, for over time, one of the outputs of AI chronolens, and we've seen that basically it creates patterns. We study these patterns. For example, we saw that the patterns that triangle, color all in magenta, and we noticed that whenever that protuberance basically marking and highlighting there, it was correlated to the fact that in the real-time series that you see in the bottom, the model is a mistake. We look at all traffic drops, and we saw that when the triangle was perfect, we went back into the training set, and we saw that there were few examples of this in the training set. So basically, the model to pick up on this pattern, and the output chronolens was an individual issue. So we generated a complex more samples, and we saw that we could train a model that was matched to the zero, the median. It has also allowed us different models with very different characteristics. And for example, here the linear, that is just a very simple one level for time forecasting with respect to STM. And what we learn is basically that of course will change this depends model to model, but basically allow to understand what pickups, for example, in very complex cases, like this prediction of load drop that is very abrupt. And for example, LLM models will not be able to pick up. To summarize, basically AI chronolens is a more sophisticated tool than legacy AI techniques that allows to benchmark models that are applied to the same data set and provide a grasp of what the model really does under the hood, and goes beyond the simple prediction accuracy, etc. We make the code public. It's not released yet because we are going to present this in a couple of months from now. So the code will be released basically very close to the conference deadline. And we make all the models available for reproducibility, what we have available, because as I mentioned, this set is basically non-open to the public. And with this, let me conclude with thanking to our funding, you for your kind attention. Thanks a lot.
Okay, volunteers. Let's keep 30 seconds of shyness and just...
Thank you for the talk. As far as I know, some deep learning models, apart from LSTM, has some inherent explainability to it. For example, attention-based models, we would have from, for example, the attention scores for the tokens. Is it something applicable to the time series as well to explain?
Yes, absolutely. It's something that basically builds on top the legacy explainability techniques. So essentially, you can replace whatever we did in the past with this more complex model and try to use the same approach. Will be slightly different than just, for example, applying LRP or SHAP, but that's definitely feasible.